It was the early 1990s. A man named Vito Broussard was knee-deep in the murky rivers of the southeastern United States, searching for something most people would never think to look for. Fossilized shark teeth. At that time, most people knew these rivers occasionally carried fossils from an ancient ocean that once covered the region. Divers would sometimes find small teeth, usually from common prehistoric sharks. Nothing special. Nothing that would change what we thought we knew. But Broussard kept finding something different. The teeth were larger. Far larger than anything typically found in these waters. Thick. Triangular. Serrated along both edges. Some of them the size of a human palm. And what made it stranger was that they weren't rare. He kept finding them again and again, in different spots, at different depths, across different sections of river. Over time, a pattern emerged. These teeth didn't belong to different animals. They belonged to the same kind of animal. A shark. But not like any shark alive in the oceans today. Something older. Something bigger. Something that the modern ocean simply does not have room for anymore. That animal is known as the Megalodon. But even with the teeth in hand, it was almost impossible to picture the creature itself. Because sharks are built differently from almost every other large predator that has ever existed. Mammals have bones. Dinosaurs had bones. Even most fish have bones. But sharks have cartilage. Not just in certain places. Their entire skeleton. Every structural element that holds the body together is made of the same flexible, lightweight material found in your nose and ears. This was an evolutionary choice, made hundreds of millions of years ago. And it worked brilliantly. Cartilage is lighter than bone, which helps a massive animal stay buoyant without constant effort. It absorbs stress during high-force movements. It bends without breaking. But cartilage has one critical flaw. It does not fossilize. When a shark dies and sinks to the ocean floor, the soft tissue disappears first. Muscle, fat, organs. Gone within weeks. Then the cartilage follows. The spine dissolves. The jaw rots away. The fins leave nothing behind. What survives is only what is hard enough to resist decomposition over millions of years. The teeth. And here is where it gets interesting. A shark does not simply grow one set of teeth and keep them forever. Over its entire lifetime, Megalodon would have produced roughly 40,000 teeth. Constantly replacing them, row after row, the way modern sharks still do today. Which means everywhere it swam, it left evidence behind. Buried in sediment. Slowly mineralized. Scattered across ocean floors all over the world. That is why we have so many teeth and almost nothing else. And it is also why reconstructing the animal requires inference. Estimation. Careful comparison. Paleontologists use the proportions of modern sharks to estimate body length from tooth size. They study jaw curvature to estimate mouth width. They examine bite marks left on fossilized whale bones. Deep, parallel gouges that match megalodon tooth spacing exactly. And from those marks, they try to understand how it actually fed. How it moved. What kind of predator it truly was. Broussard did something similar. He spent years collecting these teeth. Dozens, then hundreds. And eventually he tried to understand what they would have looked like assembled together. Using the jaw of a modern great white shark as a reference, he began arranging the fossil teeth into a full reconstruction. Not a model. Not a digital rendering. An actual jaw, built from real specimens pulled from the same rivers he had been diving in for years. And the result stopped people in their tracks. Large enough for a full-grown adult to stand inside. Lined with rows of serrated teeth, each one individually larger than anything a living shark produces today. The scale of the animal was no longer theoretical. It was visible. Physical. Standing in front of you. And once you see it assembled like that, in real proportions, the question changes completely. It is no longer, did this animal exist? The evidence is already there. The real question becomes, what kind of predator was this? How did it hunt? What did it eat? And how large was it really? For most of human history, the ocean has been a place we do not fully control. You can stand on a beach, look out at the water, and everything seems calm. Still. Manageable. But a few meters below the surface, visibility drops. A few meters more, and you are effectively blind. Sound travels differently. Pressure builds. And in that environment, size becomes invisible. A modern great white shark can reach around 6 meters. About 20 feet in length. That alone is enough to change how people behave in the water. Enough to keep swimmers close to shore. Enough to make open water feel genuinely uncomfortable. Now scale that up. Estimates suggest Megalodon reached lengths of 15 to 20 meters. Roughly 50 to 65 feet. Some analyses push that ceiling even higher. A 2025 study based on fossilized vertebral columns places the largest possible estimate at around 24 meters. Close to 80 feet. That is not simply larger. That is an animal several times heavier, with a mouth wide enough to engulf large prey in a single bite, operating in an ocean that had no answer for it. The common image is straightforward. A giant version of a great white. A bigger, more dangerous shark with the same basic shape and hunting style. But that assumption falls apart almost immediately. Because when an animal reaches that scale, it stops behaving like a scaled-up version of something smaller. Everything changes. Its metabolism shifts. Its hunting strategy changes. Its role in the ecosystem transforms entirely. And that creates a serious problem for anyone trying to understand it. Because we have no living reference. No modern predator operates at exactly that scale in exactly the same way. No complete fossil skeleton exists to confirm its body structure directly. What we have are fragments. And from those fragments, we are trying to reconstruct not just an animal, but an entire way of life. The bite force estimates for Megalodon sit at around 180,000 newtons at maximum. Let that number land for a moment. A great white shark bites with roughly 18,000 newtons. Already enough to cut through bone. Already enough to cause catastrophic damage in a single strike. Megalodon's bite was estimated to be 10 times stronger. For comparison, if you wanted to experience that kind of concentrated force through pressure alone, it would be roughly equivalent to having 3 full-grown African elephants standing on a single point. But here is what matters most. That force was not accidental. It was not simply a byproduct of being large. It was a precision tool. Megalodon's teeth were not just oversized. They were serrated along both edges, specifically designed to slice through dense, resistant material. When paleontologists examine fossilized whale bones from this period, they do not find evidence of a predator biting around its prey. They find impact fractures. Deep gouge marks cutting directly through rib cages. Consistent with an animal that targeted the structural core of large prey and destroyed it immediately. This was not an opportunistic scavenger waiting for something to die nearby. This was a predator that had specifically evolved to disable large animals as quickly and efficiently as possible. Which makes complete sense when you understand the cost of failure. Because Megalodon, unlike most modern sharks, appears to have been warm-blooded. Or at minimum, capable of maintaining a higher internal body temperature than the surrounding water. And warm-blooded predators burn through energy at an extraordinary rate. Estimates suggest that to sustain its body, Megalodon needed to consume roughly 100,000 calories every single day. About 50 times what an adult human burns in the same period. Think about what that means in practice. Every day it did not eat, it was burning through its reserves. Every hunt that failed had a real, measurable cost. Every missed strike, every prey animal that escaped, every week of low food availability pushed it closer to a threshold it could not come back from. An animal that large, in an ocean that was always shifting and changing, simply could not afford many failures. This single biological fact, that its body demanded constant, massive fuel input, becomes the thread that eventually unravels the entire story of how it disappeared. But before we get to the disappearance, there is something most people get fundamentally wrong about Megalodon. They assume it is a direct ancestor of the great white shark. That if you trace the great white's family tree back far enough, you eventually arrive at Megalodon. That one became the other. That is not what happened. Megalodon and the great white are about as closely related as a dog and a cat. They share a very distant common ancestor, an early shark lineage that diverged into two completely separate families tens of millions of years ago. Megalodon belonged to a group called the Odontidae. Giant, broad-toothed sharks that grew to enormous size over millions of years. The great white belongs to the Lamnidae. A different family entirely, which also includes mako sharks and salmon sharks. And here is what makes that split genuinely interesting. When these two lineages diverged, they made different evolutionary bets. Megalodon's family doubled down on size. They became larger and larger, eventually producing the biggest shark that ever lived. They optimized for raw power. For handling the largest prey available in warm, shallow waters. The Lamnidae went the other direction entirely. They stayed relatively smaller, but became faster, more agile, and remarkably efficient hunters capable of operating across a much wider range of ocean conditions. At the time, both strategies worked. But only one of them had a longer shelf life. Megalodon first appears in the fossil record around 23 million years ago. A time when the world's oceans were warmer, shallower in places, and rich with large marine life. Crucially, this was the age before large baleen whales. Early whales, the ancestors of modern humpbacks and blue whales, were actually relatively small by today's standards. Mostly toothed, quick-moving, and concentrated in shallow coastal waters. And Megalodon sat at the absolute top of this entire system. It hunted early whale species. It hunted large fish. It controlled the population dynamics of everything below it in the food chain, the way all true apex predators do. Its presence set limits. Its absence would change everything. For roughly 13 million years, this arrangement held. 13 million years. For context, our entire genus, all of human evolution from our earliest ancestors to today, spans only about 3 million years. Megalodon, as a species, outlasted the entire human story by 4 times over. It was not a brief experiment. It was not a transitional form moving toward something else. It was one of the most successful apex predators in the history of life on this planet. Around 5 to 6 million years ago, things began to shift. Not a single catastrophe. Not a meteor. Not a sudden event that wiped it out overnight. A slow tightening. One factor at a time. Until the combination became impossible to survive. The first thing that changed was the climate. The planet began to cool. And as it cooled, the oceans responded. Warm, shallow seas that had covered large parts of the continents began to pull back. Coastal waters, rich and productive and full of large prey, started to shrink. The geography that had supported Megalodon's hunting strategy for millions of years was quietly disappearing. And at the same time, something was happening to the whales. Faced with shifting food availability and increasing competition, a group of early whales made an unexpected evolutionary shift. They gave up their teeth entirely. Instead of hunting individual animals, they evolved baleen. Long, fibrous plates that act like biological filters. Now, instead of chasing a single seal or fish, they could swim open-mouthed through clouds of krill and tiny organisms, straining enormous quantities of food in a single pass. The logic behind this shift is surprisingly powerful. Hunting is expensive. Every step in the food chain costs energy. By going directly to the base of the food chain, these whales bypassed most of that cost entirely. More food. Less effort. And so they grew. And kept growing. With unlimited food at the base of the ocean and no predator capable of stopping adults, there was no biological reason not to. But here is what that meant for Megalodon. Its primary prey was transforming into something it could no longer efficiently hunt. Animals that had once been within its range were either disappearing or becoming enormous filter feeders operating in cold, deep water that Megalodon's warm-blooded body was not built to follow them into. And while this was happening, another predator was quietly getting better. The ancestors of the great white shark. Built for colder water. More agile. Capable of pursuing prey through environments a 15-meter shark simply could not navigate effectively. And early baleen whales, still relatively small at this point before millions of years of unchecked growth, were well within their range. What was happening, in effect, was a handover. The prey that had sustained Megalodon for 13 million years was gradually shifting. Either disappearing or transforming into something beyond its reach. And into that gap, the great white's ancestors moved in. Smaller animals filling the space more efficiently than Megalodon ever could. And Megalodon, with its enormous body burning through 100,000 calories every single day, could not wait out the transition. There is one question that always comes up when people learn about Megalodon seriously for the first time. Is it still out there? It is worth taking seriously, because the instinct behind it is not irrational. In 1938, a fishing trawler off the coast of South Africa pulled up a fish that scientists had believed went extinct alongside the dinosaurs. A coelacanth. Alive. Undiscovered for 66 million years. So the logic makes sense. If that is possible, why not Megalodon? Here is why not. Megalodon shed roughly 40,000 teeth over its lifetime. In every ocean it ever swam through, across millions of years, it left them behind. We find them on seafloors all over the world. And the most recent ones date to exactly 3.6 million years ago. Not 1 million years ago. Not recently. 3.6 million years ago. If it was still alive anywhere in any ocean, we would be finding recent teeth. We are not. Modern whales, which would be the obvious prey for a 24-meter shark, show no bite marks consistent with Megalodon. None. Not one confirmed case. And the coelacanth survived because it lives in deep water caves, barely moves, and requires almost no food to sustain itself. Megalodon was the opposite of that in every possible way. Its biology demanded constant, massive food intake. It could not hide in a cave and wait. It is gone. But here is what that absence actually means. The extinction of Megalodon did not just remove a predator from the ocean. It changed what the ocean could become. For as long as Megalodon existed, baleen whales had a ceiling. Juveniles needed to stay small, fast, and difficult to catch just to survive long enough to reach adulthood. The predator pressure was real and constant. Size had limits because size made you a target. The moment that pressure disappeared, the ceiling lifted. Unlimited food at the base of the food chain. No predator capable of threatening adults. Millions of years of open ocean ahead. So they grew. Generation after generation, with no upper limit stopping them. The blue whale. 30 meters long. The largest animal ever confirmed to have lived on Earth. It did not exist when Megalodon was alive. It could not have. It took Megalodon's extinction to create the